Hello, physics students. So today, we're going to learn about another thing that light can do. It can refract, and the phenomenon is called refraction. So to show you what refraction is, I have here a special circular tank, and I have laser light coming down through this tank. And I don't know if you could see it because the lighting isn't that great in here, but the bottom half of the tank is filled with water, and the top half is filled with air. So before I begin and show you what refraction is, I want to first review some important concepts that we already learned in the optics topic that will be important in today's lesson. The first, what is the angle of incidence of the laser light coming down on this water surface? I'm going to create a pause, and in that pause, I want you to come up with an actual number. And you don't have to write it down, just in your mind, decide what the angle of incidence is of this laser light on the water surface. So go ahead and do that now. All right, what a lot of students do is they say 90 degrees because the surface is here, the light is coming down 90 degrees to the surface. But that's not correct. Remember, all angles in optics are measured with respect to the normal, not the surface. So the normal to the surface runs straight out of the surface like this. And you see that that runs along the laser beam, or maybe we say the laser beam runs along the normal. And so the angle between the laser light and this meter stick, now this would be like maybe 30 degrees, but no, they're right on each other, so the angle is 0. There is no angle between them. So the angle of incidence is 0 degrees. Also, the laser light in the water recedes away from the surface, and that angle in the water is also not 90 degrees. It's also 0 because it's running along the normal inside the water too. So we have 0 here and 0 degrees above and below. The second thing I want to review before I show you what refraction is the speed of light. Now, in a vacuum, it's 3 times 10 to the 8th. In the air, it's approximately 3 times 10 to the 8th, a little tiny bit slower, not enough for us to detect in an optics experiment or very difficult to detect. But in the water, is the speed of light the same, greater, or less in the water? So I'm going to create a pause and pick those 3. You don't have to write it down, just in your mind decide speed of light greater, less, or equal in the water. Go ahead and do that now. You should have said the speed of light is less in the water because the index here is 1.0 and the index here is 1.33. You don't have to remember those. They're on the reference table. But you do need to know that the index in water is greater than air because of the atoms there which slow down the light. All right, so those are the 2 big ideas. What I'm going to do now is tilt this laser light to the side. It's going straight through. But what you should see is when I tilt this, the laser light does not go straight anymore. See how it comes in on this angle? Like if I take this meter stick like this, it's coming in like this. But in the water, it's at a different angle, a steeper angle. That bending is called refraction. So if I were to take this wire here, hopefully you could see it. Well, it doesn't show up that well. Let's see if I put a little light over here. Yeah, maybe that might do it. So I've got this wire like this, and in order to make it follow the laser light in the water, what I'd have to do is bend the wire like the light. And notice how I'm bending it? I'm bending it towards the normal. So we say that the light bent towards the normal. And a lot of times students get confused by that. They say, well, the light's not going towards the normal, it's still moving away. Yes, it's moving away, but it's moving away at a lesser rate. So it's moving away less rapidly, so it's kind of awkward to say. But you imagine again, if it were a wire, you would have to bend it slightly towards the normal, and it'd still go away from the normal, but not as much as before. So that's what happens when we go from low index, air 1.0, to higher index, water 1.3. But notice that there is some light that still reflects at the surface. See how there's a light comes here and then it bounces up, and there's a reflected ray up here. in the air that stays. So part of the light reflects, we have reflection. Part of it refracts, we have refraction when it goes in the water, the bending. If the index, the pattern is the opposite, instead of going from a low index to a high index, oh, by the way, I should say also, the angle down here is smaller. You probably can't see, maybe I'll get the light up here. This has numbers here, and the angle of incidence coming in is about 60 degrees right now up above. I don't know if you could read those numbers, but down below, it's only about 39 degrees. So the angle of incidence was 60, and the refracted angle was 39. So the angle got smaller because we got this bending toward the normal. But the reflected ray remains 60 degrees, just like the incident ray, because that's the law of reflection. So now I'm going to reverse the pattern. I'm going to have the light start in the water and then go into the air. And now what we see is the opposite effect. The light, rather than going straight in the original pattern, it bends in the air away from the normal and now goes up like this. So bends away from the normal. And we also still get a reflected ray in the water. So again, we have both things happening. We've got reflection, equal angles here, and then we've got refraction. Now when we go to a lower index, we went from small angle to big angle. So that's refraction, that's the pattern. Let's go to the board and summarize with some notes. So here's the title for today, Refraction and Snell's Law. Snell's Law is the equation that allows us to determine the exact angle the light makes when it goes into a second material. So here again is the summary of what we saw in the demonstration. We had light coming in a material with an index 1 less than index 2. In the demonstration, we had light coming in from air and going into water. Here I use glass, which has an even higher index, which exaggerates or makes the refraction even more dramatic for our diagram purposes. So as I mentioned, some of the light, some percentage reflects up, and then we have the angle of, the law of reflection telling us that the angle that the light comes in, if this is like 60 degrees, it'll reflect off at 60 degrees with respect to the normal. But when the light goes into this second material, what happens is rather than going in a straight line like this, it bends like this. So we say it bends towards the normal. It's not really moving towards the normal. It's still moving away from the normal here, just not as rapidly as before. It bent towards the normal. And that means that since it bent toward the normal, this angle is now smaller than the original theta 1. Theta 1 is greater than theta 2. So those are all the patterns that we saw when the light started up above. Then what happened is I showed you when light goes from a high to a low, the opposite way, like in this case, maybe we have the glass up here, and so N1 is greater now because the glass is 1.7 index and it's going into air with an index of 1.0. Then what happens, again, we have some of the light reflect according to the law of reflection. Whatever angle this is, if this is 30, this is 30 over here on the opposite side of the normal, which I show light. But now the light, instead of going in a straight line, bends away from the normal, and so bends this way. That means that now theta 2 becomes larger than theta 1. As we could see here, theta 1 is smaller than theta 2, and we say the light bends away from the normal. So let me create a pause to give you a chance to copy all these notes down. All right, before I move on, I want to just explain why this happens. Why does the light bend? Well, you may have already noticed that we're using the index of refraction, which told us that light slows down when it goes to an area where it has atoms, and the more optically dense the material is, the more it slows down. That accounts for the bending of the light. Remember, a light ray is just like a thing we invented to help us understand or analyze what's happening in optical situations. But what really is coming down here are transverse waves with a bunch of crests that run perpendicular to the ray. And so I could represent that with this paper arrow. This would be the leading crest, and there's a bunch of crests coming towards the glass like this. Now watch what happens. This entire crest doesn't enter the glass at the same time. The part that enters the glass first is this, the right edge or the bottom edge of this wavefront. That means that this part of the wave slows down because it's inside the glass index refraction, as we learned in the last video. Whereas this is still in the air. So it's still moving faster than this. And what happens to a wavefront if the right side slows down while the left stays going fast? Well, I could do that like this by pulling this here, going faster. You see how that's going to turn it? And then eventually when it all gets in, now these two, this entire wavefront is completely in the glass, so they both have the same speed again, so they go in a straight line like this down. But while that entry occurred, the bottom part slowed down first while the top went fast. That turns it like that, and then it goes straight. The opposite effect happens over here. This wave front comes down, and it's going in the glass, which has a high index, so it's going relatively slow. Then what happens is this lead edge gets into the air first. So this lead edge, the bottom part, or the left side, whatever you want to call it, or from the light's perspective, maybe the right side, but this part speeds up while this part's still slow. And look what happens when I speed this up faster than this. I'm going to turn that light wave as it's coming down. It turns, and then once the wave is completely in, then it'll go the same speed in a straight line like that. So it's all because of the speed changing on different parts of a wavefront. That's what causes that bending. All right, as I said, there's an equation that tells us exactly how much this bending occurs. That's Snell's law. So here it is. N1 sine theta 1 equals N2 sine theta 2. So first thing, of course, that's on the reference table in our wave section. So here's our wave section of the reference table, and here's the equation that I just wrote on the board. So you could find that right in the reference, N1 sine theta 1 equals N2 sine theta 2, wave section of the reference table. The concepts that we discussed over here are actually embedded in this equation. Let's suppose we've got a certain N1 and a certain theta 1. If N2 is bigger than N1, theta has to compensate and go down. That's what we saw over here. We went to a higher index, smaller angle. If we have this situation where we go from a high index to a low, so this went down, then that means the theta has to go up for the equation to hold on the other side. So we had here bigger index, a smaller index, bigger angle, compensate in that equation. So, nice equation. Let's do an example. We'll do one example here. So here's the example. We've got a flint glass in a block of flint glass, that's this rectangle, in water, submerged. The light's coming down is indicated. We want to determine the angle in the second material. And then part B, we want to construct the rays of the reflected and the refracted rays. I didn't want to write it out because I wanted to conserve a little space on the board. So that's what we're doing. Let me create a pause to allow you to copy this and the example down. All right, so I need to make some room. And then the first thing that we do in the Regents curriculum, on the Regents test, is we always write out the equation without any data in it. So let's begin with our equation. All right, so the next thing we have to do is plug in our numbers with the units. So the first thing, N1, the light begins in medium 1, which is water. So we have to find the index of refraction of water. That's page 2 of the reference table. And water is right here, okay, 1.33. And by the way, while I'm here, we also need the index of refraction of flint glass. So we look here and we see glass comma flint, 1.66. So those are the two values, 1.33 and 1.66, that we're going to use in this problem. So again, most of the time, unless you're solving for this as an unknown, one of the indices, you look these up on the reference table. So let's go ahead, 1.33. But here's the thing. If I put 20 degrees, I get the wrong answer. So why did the problem give you 20 degrees? As I said, the Regents will often do that to try and trick people. Because remember, the angles in all optics are supposed to be measured to the normal. So here's the normal, all right? So there's the normal. So I want the angle with respect to that line, not the surface. So this is 90 degrees. And if this is 20, that's the other part of 90. So that's 70 degrees. That is actually the number we plug into Snell's law. Remember I said with the law of reflection, it didn't matter if you said, okay, let's make it 20 degrees to the surface, you get the same ray. But this time, if you plug in 20 here instead of 70 and you solve for theta 2, you will get the wrong number, the wrong angle. So it has to be, in Snell's law, the angle with respect to the normal. The second material is flint glass, as I said, you know, that's the 1.66. And then theta 2 is the unknown, what the angle is in the flint glass. So now we just have to do a little algebra. If we punch this on a calculator, we get 1.25, 1.25, three significant figures, equals 1.66 sine theta 2. So what I'll do is divide both sides by 1.66. And by the way, the index has no units. So you see I don't put units? But here's the thing, very unfortunate on the Regents. This counts as a unit. If you leave that little tiny thing off and you get the answer correct, even though it looks like you should get like maybe 90 on this problem, the Regents scores this as a 1 out of 2, an F of 50% for leaving that little degree off. So very brutal grading, but don't do that on the Regents, you'll lose a lot of points. All right, so then this, when you divide it out, comes out to be 0.753 equals sine theta 2. Oh, not that. And then so what we have to do is do the inverse sine of both sides, theta 2, and I don't even have to write this, but I just want you to have it in your notes so you see where it came from. And punch that on the calculator, and you get 48.8 degrees. There it is. Okay, so let me create a pause to give you a chance to catch up with these notes if you need it. Okay, next thing, part B, construct the rays. As I said on the Regents, you have to be able to draw these rays correctly to the proper angle. So let's start with the reflected ray. What we have to do is measure, this was 70, so the reflected has to be 70. That's the law of reflection. So remember I said, my protractor has numbers on it. I haven't gotten around to scratching them off, but yours, the paper ones, hopefully don't have numbers. You're using the ones I had you print out. So we don't use any of the numbers on the protractor. We count away from the normal, 10, 20, 30, 40, 50, 60, 70. No, that's not right. Yeah, 70, there it is. Yeah. Put a little light mark. Now notice, my numbers are 20 and 160. There's no 70 here. That's why I say the numbers on a protractor, just misleading. Use it just to count over degrees. Now I'm going to grab a straight edge. And again, this is tricky with chalk. The chalk's so thick. All right. Oh, see, there we go. It's a little sloppy. All right, so I'm going to label this the reflected ray. Regents likes these things labeled, 70 degrees. All right, so there's the reflected ray. So go ahead and do that now. By the way, I should have mentioned, I hope that when you drew out the example, you drew this very accurately. If not, you're going to have to try and go back and fix it so that, you know, this really is 20 degrees, this is 70, so on and so forth, and this is nice and parallel. All right, so go ahead and copy that diagram now. All right, next thing, the angle of refraction, 48.8. So I have to first create a normal. So that's right here. So there's my normal. Okay, and then I'm going to measure 48.8 from that normal, ignoring the numbers on the protractor. 10, 20, 30, 40. There's 50, so 48 will be right around there. Okay, so get my ruler out. So go ahead and draw that refracted ray as accurately as you can now. All right, so that was refraction, bending of light towards or away from the normal, depending on whether you go to a higher or lower index. Go back in the diagrams that you drew over here that I erased. Make sure you understand everything, the reflected ray, how that works, the refracted ray, whether it bends towards or away from the normal, and then Snell's law. This is how you calculate that second angle, whether you're going from a higher to lower index. Plug in the indices, the theta, solve for what's unknown. And of course, being able to draw these things accurately is also part of the curriculum. You have to be within a degree or two off, depending on how the answer key goes, how accurate you have to be. So that's it. That's refraction. Just a reminder. So refraction is with an R. Refraction. We had reflection and diffraction. Remember, diffraction is a light wave that bends and spreads when it goes through an opening that's narrow compared to the wavelength. This is why we know reflection here and we know refraction. So reflection, diffraction, refraction are the three kinds of behaviors of waves in the Regents curriculum. All right, so I hope you enjoyed the demonstration. I thought it was very beautiful, again, with a nice glowing laser light. I hope you enjoyed the physics, the concepts, the equations, the calculations, and the video. I'll see you in the next physics video.